Now you might recognize these expressions as the div, and that would look something like this. Might have arrows pointing out. That would be the div. And so you take this vector differential operator right here, and you dot it with the fields that we have. So that just means that you're going to take the partial differentials in all 3 dimensions, and then you add that all up because it's a dot product, so you get a scalar quantity, just a number. And if you look at this, if the size, we're just measuring the size of the arrows. So if the size of the arrows are bigger going out, then it's positive. If it's bigger going in, then it's negative, because there might be some arrows going in too, right? There might be some smaller arrows going in, but if we look at the net there, the net is positive, and so therefore the div is positive. That's the div. Now these expressions you might recognize as the curl, and that would look something like this. You could think of it as some arrows rotating around a particular point. This could be the curl. And that's kind of like how fast something is rotating around a particular point. So you take the same differential operator with these fields, and you'll get a 3D vector. And you can think of it as the velocity in each of the 3 dimensions, how fast it's rotating, rotational velocity. That's the curl. Now, some scientists found that these expressions can actually describe the laws of electricity and magnetism. The first step is to transform these into the divergence theorem and Stokes theorem. So here we'll take some integrals. We're going to do a triple integral for these ones over dv. 1, 2, 3. Triple integral over dv, and we'll set that equal to a closed integral of our field dotted with dA. And over here it's going to be the field dotted with dA as well. And then here this will become Stokes theorem. So we got double integral over the dA on both sides. And these will become our field dotted with dL and the field dotted with dL. Well, we should probably remember that the dot products and the cross products involve sines and cosines. So in this case, this would be when cosine of 0, that's going to be equal to 1. So that'll make things nice over here. And in this case, we're going to be looking at when sine of 90 degrees equals 1. So things will be nice there as well. But things might start to look a little bit more familiar at this point. See, because what this is really trying to say is that this is the electric field times the area, and this is the magnetic field times, and this is the magnetic field times the area. And then these would be more like, well, again, the electric field here. And this is going to be multiplied by not an area, but rather a circumference, a line. So 2 pi r would be lengths of loops, for example. And in this case, we would be taking the magnetic field, which is the B. It's the magnetic field. And we'll multiply that by a 2 pi r. So this is essentially what these things are trying to say. Now we could recognize this one here maybe as being equal to electric flux, right? And this one, we could also recognize that one as being equal to magnetic flux. So that might be more recognizable. And then this one, well, electric field times distance, E times X equals voltage. That's V. So that's induced voltage, induced EMF. Well, this last one doesn't really have a nice symbol that we can represent it, but it does have mu naught and then I enclosed plus mu naught epsilon and then the time derivative of the electric flux. So now we can kind of start to see what these equations might represent. Now Gauss's law for electricity states that this equation is equal to Q enclosed divided by epsilon naught. And maybe it's better to draw this, because what we're trying to say is if we have an area that's enclosed, so let's say there's a little enclosed area. This is an imaginary area. And then there's a charge in there. Well, isn't that charge just going to have little electric field arrows pointing out of it? Well, we can determine this area to be the area of that sphere. So we can basically say that the electric field is going to be equal to the Q enclosed divided by epsilon naught times the area of a sphere, which should be 4 pi r squared. So what this allows you to do is basically draw different radiuses, but it'll allow you to calculate the electric field at that particular radius. So this would be the electric field at that radius, the electric field at that radius. So you get the area of that sphere. These are the Gaussian spheres that you can, allows you to calculate the electric field. The next equation is Gauss's law of magnetism, which simply says that this is equal to 0. And that's only for an enclosed area. Both of these things are closed integrals. Well, what that's really trying to say is, let's say we drew a little magnet here. And this is a plus side, that's the minus side. So we'll have the plus side and the minus side there. And you would imagine some little magnetic field lines coming out of these. Of course, this is going from positive to negative. The point is that if you try to draw a sphere around this, well, you're not going to get any flux, because what goes in comes out, and even if this stuff were to extend outwards, they would just simply come back in anyway. Well, what this is really trying to say is that there's no magnetic monopoles, and that means that all magnets have the pluses coming out and the minuses going in. You're never just going to find a magnet with just a plus or just a minus like you would with the charges. So that's the main differences between these two equations. Well, Faraday's law of induction states that this equation is equal to the negative time derivative of the magnetic flux. Well, what that's really trying to say is, let's say we had a loop of wire. So here's your loop, and I'm going to give it some coils here. So you usually have to keep track of that by multiplying this by the n. But let's say we had a little magnet, and we were moving the magnet inside of this coil, and what would that we'd move it back and forth like this, and what that would do is it would increase or decrease. It would change the magnetic field. It would do something to that magnetic field, and so you'd get some sort of basically you get a current here. So if you're going to increase the magnetic field here, notice that this is increasing field. This is B plus right here, because the magnetic field is increasing when we're maybe moving the wire magnet that way or something. This would give you a negative induced EMF, and the induced EMF would give you then a current going in this direction. Because what would happen is you're going to need to counter this growth of that magnetic field. So usually you would require a magnetic field would increase this direction, giving you a current going into the wall here. So you'd have to counter that by making it go this direction, and that's what's given. That's what the negative symbol is for. So it would come out of the wall, and that would sort of basically prevent or counter this growth. So if this was the induced current, then we could have the relationship that as the magnetic field increases, magnetic field is increasing, that means that we'll get a negative induced current. And so we could rearrange this equation to say that the induced EMF is equal to the negative time derivative of B times A, where A is this area right here, that the magnetic flux is going through, and this is the time derivative of that magnetic flux. And we can also calculate the current that we have there by dividing the induced EMF by the resistance in this wire. So that's interesting. But that's only one thing that you can do with this. But there's another way we can change the magnetic field. In this case, we just moved a magnet around. But let's set up a scenario where we have two coils, one on the inside and a bigger one on the outside. And the outside one is going to have a changing current. So we're going to increase this current, make it really, really strong over time. And that's just going to basically change the magnetic field inside, because that magnetic field is going to increase. And that really comes from this next law right here, but we're taking advantage of that. So we're increasing the magnetic field here. We're changing the magnetic field. And basically that's going to do the same thing on the inside there. So that's going to increase, that's going to cause an induced current in this direction because of the induced EMF. So the EMF comes first. Let's just keep that in mind. But in this case, we are going to calculate something a little different. We're going to try to solve for the E as well, because we already calculated the EMF over there and the current. But let's also calculate E, because there's something else you could do with this. So first, let's write that relationship that we have. We've got the current coming through this direction, and this is going to be a B going up, and that means that the magnetic field is increasing, and then we're just going to get the negative induced current in this direction. Okay. But let's try to solve for E, because we can say that E is going to be equal to the time derivative of B times A divided by the 2 pi r. So the electric field at this radius right here that we've distinguished from that particular coil is going to be calculated by this equation. Similarly to what we did there. It's all about these sort of imaginary loops or physical ones if you want to. But they don't really have to be physical. They can also just be imaginary. And then over here we can also state that the induced EMF is equal to, well, this is the craziest thing. You can also change the area rather than the magnetic field. So that's just another way that you can use this particular law. So technically we have three ways. We can use this way right here. We can use this way right here, telling us the electric field. We can also change the area. So there's just three crazy applications of Faraday's law of induction. Now this part of the Ampere-Maxwell displacement law is pretty simple. It's just saying that if we have a wire and there's a current going through that wire, then there is going to be a magnetic field. And so you get that right here. It would follow the right-hand rule. So it goes into the page here and out of the page here, and that we'll call B naught. Now you can calculate what B naught is at different points. We'll just calculate it for at this particular radius right here. This would be the radius RC. Now we can draw an Amperian loop right at that particular radius. We'll call that R naught, where that equals the radius of that wire so that we can calculate what the magnetic field is at the exact radius. We'll be able to say that B naught is equal to mu naught I enclosed divided by 2 pi RC. So that's how you can just find the magnetic field at the radius when the Amperian loop radius equals the radius of the wire. The second part of Ampere-Maxwell displacement law is essentially telling us that if we start to change that current, then we're also going to change the magnetic field. So that makes sense. Let's just draw that wire. And here's that current, and we're going to start increasing the current. So we'll increase the current. Naturally, that's going to give us more of that magnetic field. So we can sort of see how we would have that original magnetic field, and we're going to start to add more of it as we increase that current. It's basically what that is trying to say is that we're just changing the magnetic field. And again, this radius would be RC. We'll notice that this symbol is the electric flux symbol, and that contains the electric field. So we're really changing the electric field to be able to create this magnetic field. And what's a way that we could change the electric field but with a charging or discharging capacitor? So we could state that, first of all, this particular quantity here is really called the displacement current. So we'll say that ID is equal to epsilon naught and then the time derivative of EA. But if we have a charging capacitor, then IC is equal to ID, or discharging, right? And this is the displacement current. That's where we would get this displacement from. And we could try to draw this capacitor. So here it is. And here is the radius of the capacitor. Now as we start adding or removing charges from these surfaces, then that electric field in between there is going to change. And so now you'll be able to essentially draw Gaussian spheres anywhere you want to. You can draw a sphere here, you can draw it on the perimeter, you can draw it out here, and those are going to be your R naughts. So basically, if you're trying to calculate what that magnetic field is at those particular points, just kind of like we did before, here I just said R naught is equal to RC. That's on that on the perimeter. But let's say you wanted to find the magnetic field inside the capacitor, and you'd have to use this formula. It'd be mu naught ID divided by 2 pi RC. That's the capacitor radius there, squared. And then you'd have to multiply that by the R naught. And this is if you're inside the capacitor. Or R naught is actually less than RC. You can use that equation. But let's say you're outside over here. In that case, you'd have to use this equation. B naught is equal to the mu naught ID divided by 2 pi, and this is R naught right here on the bottom. And this equation is for when you're outside the capacitor, or when R naught is greater than the RC. And so these are some basic ways that we can view these Maxwell equations. So all these equations, except for this little portion, had already been known by the 1830s. But 30 years later, Maxwell came and added this little bit. And that's how we discovered that there was a relationship between the magnetic field, the electric field, and the speed of light. Because look, we have that changing electric flux. The changing electric field gives you a magnetic field, right? But over here, we've noticed that changing the magnetic field gives you an electric field. So that means that you're trading between the electric field and the magnetic field, and those are constantly shifting back and forth. So in the next video, we'll take a look at how Maxwell was able to combine the changing electric field and magnetic field into one equation, which produced an electromagnetic wave equation. And when calculated in a vacuum, was propagating at the speed of light. And so that was what was predicting light waves. That's crazy.